Nobody told you the truth about what Voyager 2 actually found. They announced it like a celebration, a press release, a headline. But buried inside the data that came back from 13 billion miles away was something that quietly dismantled 50 years of scientific certainty. The boundary they said existed, the one they named, mapped, and taught in every university on Earth, did not behave the way they said it would. And the boundary they said did not exist. Voyager 2 crossed it anyway. What is out there is not what we were told, and the silence from the scientific community since then is louder than any signal Voyager has ever sent home. There is a spacecraft right now, at this very moment, traveling through a region of space that no human being has ever seen, that no telescope can reach, and that no model built on Earth fully predicted. It is moving at roughly 34,000 miles per hour. It has been moving for nearly 49 years without stopping, without turning around, without rest. As of January 2026, Voyager 2 is more than 13 billion miles away from the Earth. And the data it is still sending back, even now, even as its power slowly dies, is rewriting what scientists thought they knew about the edge of everything. Think about that for a moment. 13 billion miles. The light from the sun takes 8 minutes to reach Earth. A signal from Voyager 2 traveling at the speed of light takes over 16 hours to arrive. By the time engineers at NASA's Jet Propulsion Laboratory receive a command response from the spacecraft, an entire day has nearly passed. We are not talking about a distant satellite. We are not talking about a probe orbiting another planet. We are talking about a machine built with 1970s technology, powered by a nuclear generator the size of a garbage can, communicating across a distance so vast that the human mind cannot genuinely process it. And yet, it is still talking, still sending, still discovering. And what it has discovered has changed the conversation in ways the headlines never quite captured. But here's where it gets complicated. The story of Voyager 2 is not simply a story about distance. It is a story about a boundary, a specific boundary, one that scientists spent decades theorizing, modeling, debating, and ultimately naming. They called it the heliopause. They described it as the outer edge of the heliosphere, the enormous protective bubble of solar wind and magnetic energy generated by our sun, a bubble that surrounds our entire solar system and stretches in all directions far beyond the orbit of Pluto. Inside that bubble, the sun's influence dominates. Solar wind flows outward, cosmic radiation from deep space is partially deflected, and the electromagnetic fingerprint of our star can be felt in every corner of that vast interior. Beyond that bubble, everything changes, or so the theory said. The reality, as Voyager 2 revealed, was far more unsettling. The boundary, called the heliopause, is where the tenuous, hot solar wind meets the cold, dense interstellar medium. Scientists had built elegant theoretical models describing exactly how this transition would occur. They expected a sharp, clean edge, a defined line where the sun's domain ended and interstellar space began. They expected temperatures to rise sharply on the other side. They expected the magnetic field to shift dramatically in direction as it aligned with galactic forces rather than solar ones. They expected, in short, a boundary that behaved like a boundary. What Voyager 2 found instead was something that forced researchers to pause, look at their data twice, and quietly begin rewriting their models. Perhaps most surprising of all, Voyager 2 found that the magnetic field beyond the heliopause remained closely aligned with the field inside the solar system, challenging several expectations about how this invisible boundary would behave. Read that again. The magnetic field did not shift. It did not realign with galactic forces the way the models predicted. It continued in the same direction, with the same orientation, as if the boundary had not fully interrupted it. What most people are not seeing in this discovery is what it actually implies. It implies that the heliosphere and the interstellar medium are not simply two separate realms with a clean dividing wall between them. They are interacting. They are leaking into each other. The boundary is not a wall. It is more like a shoreline, where two oceans of entirely different temperatures and compositions are constantly pushing against each other in ways that shift, breathe, and change. And this is where everything changes, because the models that predicted the heliopause were not minor calculations done in someone's notebook. They were the foundation of our understanding of how the sun protects life in the solar system. Voyager 1 discovered that the heliosphere protects Earth and the other planets from more than 70% of cosmic radiation. 70%. More than 2/3 of the deadly high-energy particles streaming through interstellar space at nearly the speed of light, particles capable of damaging DNA, disrupting electronics, and stripping the atmospheres of unprotected planets, are blocked by the heliosphere before they ever get close to Earth. That protection is not a given. It is not permanent. It is a dynamic, living shield generated by our sun, and it fluctuates. It breathes. And, according to the data that Voyager 2 sent back from beyond its edge, it does not end where we thought it ended. The new papers confirm that Voyager 2 is not yet in undisturbed interstellar space. Like its twin Voyager 1, Voyager 2 appears to be in a perturbed transitional region just beyond the heliosphere. A perturbed transitional region. That is scientific language for something nobody fully expected. There's a zone out there, beyond the heliopause, beyond the boundary that was supposed to mark the end of the sun's influence, where the environment is still being disturbed by forces connected to our solar system. The clean division between inside and outside does not exist the way the textbooks described. What exists instead is a layered, complex, contested region where solar energy and interstellar material wrestle against each other in a struggle that has no clear winner and no clean edge. But here is what the mainstream narrative almost entirely missed. This was not the only boundary that surprised scientists. There is another layer to this story that requires going back years before Voyager 2 ever reached the heliopause, back to a region called the termination shock. Prior to crossing the heliopause, Voyager 2 crossed a region known as the termination shock back in 2007, where the speed of the solar wind dropped dramatically as it began to encounter interstellar particles and radiation. At the termination shock, the solar wind, which had been streaming outward from the sun at supersonic speeds for billions of miles, was suddenly forced to slow down dramatically as it collided with the pressure of interstellar space pushing back. The sun's outward breath meeting resistance, and what happened at that boundary was already deeply strange. The first surprise was an unexpectedly strong magnetic field in the surrounding interstellar region, generated by currents in that incredibly tenuous gas. This magnetic field is squashing the bubble of outflowing gas from the sun, distorting it from the uniform spherical-shaped space physicists had expected to find. A second surprise emerged. Just outside that boundary, the temperature, although hotter than inside, was 10 times cooler than expected. Theorists had to scramble to come up with an explanation for the unanticipated chilling effect, 10 times cooler than expected. That is not a minor discrepancy. That is not a rounding error. That is a fundamental failure of the existing models to predict what actually exists at the edge of our solar system. And here is the detail that should have received far more attention than it did. While Voyager 1 apparently made a single crossing, Voyager 2 apparently crossed the boundary 5 times. 5 times. The boundary was not stationary. It was moving, oscillating, pushing back and forth like a membrane responding to pressure on both sides. The edge of our solar system is not a fixed point in space. It is a dynamic, breathing, living threshold that shifts with the rhythm of the sun's activity. Think about what that means. Every map ever drawn of the solar system, every diagram in every textbook, every illustration showing a clean spherical bubble around our star, all of them were approximations. Useful, perhaps, as rough guides, but fundamentally incomplete. The real boundary is alive, it moves. It fluctuates with the 11-year solar cycle, expanding when the sun is more active and contracting when the sun is quieter. Fluctuating solar activity made the boundary oscillate, so the spacecraft ended up crossing the termination shock several times. The cosmic frontier is not a wall, it is a tide. Now, consider the timeline of this mission in full, because the scale of what Voyager 2 has accomplished demands to be stated with total clarity. Voyager 2 was launched on Aug 20, 1977, and NASA planned for the Voyager spacecraft to take advantage of an alignment of the outer planets that takes place only every 176 years. Once every 176 years, the planets arrange themselves in a configuration that allows a spacecraft to slingshot from one to the next, using the gravitational pull of each world to accelerate toward the next without expending additional fuel. That window existed in 1977. NASA seized it, and Voyager 2, following that once in nearly 2 centuries path, became the only spacecraft in human history to fly past all 4 of the solar system's outer giants: Jupiter, Saturn, Uranus, and Neptune. At Uranus, Voyager 2 discovered 11 new moons and 2 new rings. It also discovered the Great Dark Spot, a massive storm at Neptune, and confirmed that Neptune also has rings. These were not minor scientific additions. These were entirely new worlds revealed for the first time in human history, visible to human eyes and instruments only because a team of engineers and scientists in 1977 recognized a 176-year window and jumped through it. But the planets were just the beginning. What no one fully anticipated was that Voyager 2 would still be doing science nearly 5 decades after launch, that it would reach the edge of the solar system, cross it, and begin transmitting data from the other side, and that the data from the other side would force a complete reassessment of fundamental assumptions. According to informed sources within the scientific community, the findings from Voyager 2's crossing were not simply surprising in isolated ways. Taken together, they suggested that the heliosphere is not the passive, static shield it was assumed to be. It is an active, dynamic structure whose boundaries are shaped by forces both inside and outside our solar system simultaneously. Here's a detail that brings this into sharp focus. The plasma inside the heliosphere is hot and sparse, while the plasma in interstellar space is colder and denser. The space between stars also contains cosmic rays, or particles accelerated by exploding stars. Cosmic rays. Particles born from stellar explosions, from supernovae that happened thousands of light years away, accelerated to nearly the speed of light and hurled across the galaxy in all directions. They arrive constantly, invisibly, relentlessly. And the heliosphere, this enormous bubble our sun has been inflating for billions of years, deflects the majority of them away from Earth. But the boundary that does this deflecting is not where we thought it was. It is not shaped the way we thought it was shaped. And that has implications that reach far beyond academic interest. The real story is this. If the heliosphere is more irregular, more dynamic, and more permeable than the models assumed, then questions arise about long-term protection. If the interstellar medium is becoming more unstable, or if the solar wind of our sun is diminishing, it may be that one day our planet will be exposed to lethal cosmic rays in much larger quantities. That is not a sensational claim. That is the natural logical consequence of what Voyager 2 revealed. The shield has weaknesses. The boundary fluctuates. The protection is not guaranteed at the level we assumed. And understanding exactly how this system works, where it is strong and where it is thin, matters enormously for long-term models of Earth's habitability and the survivability of spacecraft, and eventually humans in deep space. And now, right now in 2026, the story is entering its final chapter. And the urgency of that reality is something the scientific community is grappling with in real time. NASA engineers at the Jet Propulsion Laboratory have shut down the cosmic ray subsystem experiment on Voyager 1 as of February 25th, and plan to turn off Voyager 2's low-energy charged particle instrument on March 24th. Instruments are being turned off, not because they stopped working, because the power to run them is running out. Voyager 2 is over 13 billion miles from Earth. Its cosmic ray subsystem is scheduled to be shut off in 2026, this year. The instrument that measures the very cosmic rays that Voyager 2's crossing revealed to be more complex and more present than expected, that instrument goes dark this year. Every shutdown is a narrowing of vision. Every instrument switched off is a set of questions humanity will never be able to answer with this mission again. With the implementation of this power conservation plan, engineers believe the two probes could have enough electricity to continue operating with at least one science instrument into the 2030s. One instrument. A machine that launched with 10 scientific instruments, that flew past 4 planets, that crossed the termination shock and the heliopause, will spend its final years in the dark between the stars with a single sensor still listening. It is an image that deserves a moment of reflection. Because what Voyager 2 is doing out there, surviving, transmitting, collecting, is something no other human-made object has ever done and may not do again for decades. There is no other active spacecraft in interstellar space positioned to observe the same region from the same angle. No replacement mission is ready. No follow-up probe is in that neighborhood. When Voyager 2's last instrument goes silent, a window of direct observation that took 49 years to open will close. But here is what makes this genuinely fascinating rather than simply melancholy. The science does not stop when the spacecraft goes quiet. The data already collected from Voyager 2's crossing is still being analyzed, still being compared to models, still producing papers and revisions and surprises. IMAP, the Interstellar Mapping and Acceleration Probe, launched in 2025 and is described as IBEX on steroids, with the same basic capabilities but at higher resolutions and taking additional measurements. A new generation of instruments is now trying to map the heliosphere from the inside, using the data Voyager collected as a foundation. The findings from a spacecraft built in the Nixon administration are now guiding the design philosophy of 21st century missions. That is how significant the Voyager data has been. It was not merely a first look. It was the only look, and everything that comes after builds on it. What most people are not seeing is how these findings connect to something even larger. The heliosphere is not unique to our sun. Every star generates one. Every star in the Milky Way, every star in every galaxy, creates its own bubble of influence and protection, pushing against the interstellar medium, creating boundaries, perturbed transitional regions, zones of contested space between the stellar interior and the vast cold dark, between the stars. And every civilization, every biosphere, every planet that might harbor life is dependent on the stability of that bubble. What Voyager 2 taught us about our own heliosphere is a template, imperfect, contested, still being refined, for understanding what it means to live inside a star's protection anywhere in the universe. People tend to think of interstellar space as empty, but it is actually full of charged particles, atoms, molecules, and plenty of dust. Cosmic rays are high-energy particles that whiz through space at nearly the speed of light, and they are much more abundant in interstellar space than in our solar neighborhood. The space between stars is not empty. It never was. It is a different kind of full of radiation, of particles, of forces that our instruments are only now beginning to measure directly. And the boundary between that space and the space inside our heliosphere is where the most important questions about our place in the galaxy are being decided, one data point at a time. It will take about 300 years for Voyager 2 to reach the inner edge of the Oort cloud and possibly 30,000 years to fly beyond it. 30,000 years. Long after every human now alive has died, long after languages have changed and civilizations have risen and fallen and risen again, Voyager 2 will still be traveling. It will cross through the vast shell of cometary bodies at the solar system's outermost edge. It will continue into the deeper dark. It carries a golden record with greetings in 55 languages, sounds of Earth, music, images, a message to whoever might find it, a bottle thrown into the most unfathomable ocean imaginable. And the odds of it ever being found are so small as to be effectively zero. And yet it was sent. Because the mission was never simply about science, it was about the kind of species we want to be, the kind that reaches, the kind that asks, the kind that sends a message even when there is no guarantee of an answer. But perhaps the most haunting part of all of this is not what Voyager 2 found. It is what it could not find. The boundary it crossed was not the end of the solar system. Not really. The heliosphere is just one layer. Beyond it lies the Oort cloud, a theoretical shell of icy bodies so distant it has never been directly observed by any spacecraft, because no spacecraft has ever reached it. Beyond the Oort cloud lies true interstellar space, the region where even the sun's gravitational influence begins to thin and compete with the pulls of other stars. Voyager 2 is in the outermost envelope of that transition. It has passed the heliopause, but has not escaped the sun's gravity. It is, in the most literal sense, in between, in a region that belongs neither fully to the solar system nor fully to the galaxy. A frontier with no name, no map, and no precedent. This is not chaos. This is revelation. Every strange reading, every temperature that didn't match the model, every magnetic field that refused to shift the way the textbook said it should, all of it is data. All of it is the universe correcting us, redirecting us, showing us that the questions we thought we had answered were only the first layer of a much deeper stack of unknowns. And in 2026, as instruments are powered down one by one, as the signal grows slower and the power grows dimmer, the window is closing, not on the mission. The mission, in the truest sense, never ends. The data will be studied for generations, but the window of active discovery, of new measurements from that specific location in space, that window is narrowing in real time. What happens when Voyager 2 finally goes silent? What questions will remain unanswered because the only instrument capable of answering them was 13 billion miles away and running on fumes? And what will it mean decades from now if we build a faster spacecraft, one that can reach the heliopause in years rather than decades, and it finds something that Voyager 2's aging sensors were too limited to detect? What if the boundary is stranger still? What if the perturbed transitional region is larger, more complex, more significant than even the revised models suggest? What if the heliosphere, our shield, our cosmic home, is changing in ways that demand urgent understanding rather than patient analysis? Voyager 2 did not just cross a boundary. It revealed that the boundary was never quite what we thought it was. And that revelation, quiet and enormous and still unfolding, is perhaps the most important thing a 720-kilogram spacecraft launched during the Cold War has ever given humanity. Not the images of Neptune's storms, not the discovery of Uranus's rings, but the simple, devastating, awe-inspiring truth that the edge of home is not a line, it is a question, and we are only beginning to understand how to ask it.